Hi! Crash Course Physics episode 3 is out. This week it was all about integrals. And we even got an explanation for the kinematic equations from 2 weeks ago. All in all, it was a well done episode. Here I want to share a few comments on the geometric picture behind integrals and why we use them in physics to represent way more than just areas. First of all, why does the area under a curve have anything to do with derivatives? Because a small change h in the variable means that a small rectangle h times f of x gets added to the area. So f of x is precisely the derivative of that area. In other words, the height of the graph is the area's rate of change. But be careful, this means that whenever f of x is negative, the area counts as negative also. Let's look at an example from physics. When we plot the electric current flowing through a wire against time, the area under this curve will be of the unit amperes times seconds, which are coulombs. It may be a bit weird to equate an area with an electric charge, but we use areas in infographics all the time to represent all kinds of quantities. The scales chosen on the axes determine the conversion factor. In the simplest case, the current is constant, and the charge is simply the area of the rectangle, I times t. And if the current is alternating in a sinusoidal fashion, as in a power outlet, the charge transported is behaving like a sine curve as well. And if you play around with the power setting on your microwave as it is running, you affect the heat energy delivered to your food. You could in principle integrate any function by drawing it out on the power setting and then measuring how hot your food is. Or draw it out with your water tap and measure the volume of water you have collected. The integral of constant gravitational acceleration is v equals v0 plus g times t. The constant v0 is the initial vertical velocity. If you throw the ball upwards, for example, the velocity will first have to decrease to a full stop before picking up a downward direction. Now let's integrate that to get the position. Wait a minute, now the area and the velocity curve represents position? Weird, right? But yes, the units check out. We see that the position first increases as long as the velocity is still positive. But as it decreases, the ball decelerates to a full stop. Then the change in position becomes negative. The ball eventually crosses the starting point and falls further downwards. Add to the whole thing the initial position, that is, the integration constant in that second step, and you've got the second kinematic equation.